And Nicholas. And let's see who that was. Fabian. So all we're missing are Zach Price, Ibrahim, and Mark. All right. Oh, what happened to my, I didn't do that. Okay, so what we're gonna do here is we're gonna go back a little bit. Semiconductor physics day 2. Somehow I forgot to do that. Control C. Where is it? Where's my other one? Somebody chatting at me. Control V. We'll just have to make this all white. So we can read it. Okay. And we can skip over that. So no labs on Wednesday, no labs on Friday. Your next assignment is due Monday. It's a pre-lecture quiz and homework 8. And somebody chatted at me, so I need to check that. I am here. Mark's here. Yay. Okay, so all we're missing now is Ibrahim and Zach Price. Okay. What's going on? Lab 5 will start next week, not this week. No lab on Wednesday. Get a little bit of break from lab. Catch up on your other assignments, and you can maybe like finish up lab 4 and all that good stuff. This class, I see that. This is the last big topic we have. After the next exam, we're going to start looking at BJTs. They're mostly useful for discrete design if you need like a pass transistor for your capstone project or something like that, where you're doing a board level design. Inside of integrated, or if you're doing analog circuit design, like you're working for TI down in or on semi in Tucson or Phoenix, places like that, you're doing analog design, you might use BJTs. But for most of the world, MOSFETs are what are used in pretty much every digital design. If you go someplace like Micron, where they're dealing with a very digital chip, a computer memory, you'd be surprised by how many analog circuits are actually in there. There's charge pumps, there are op amps, there are sense amps, there are analog line drivers, there's level shifters in there too. There's a lot of mixed signal stuff even inside of a memory chip. They have to do it all with MOSFETs, even though they're not quite as good at analog applications, because the process that they're building them for, that builds the big memory array, is all CMOS. And so we're going to start with MOSFETs today. We're going to talk about MOSFETs first off as if they are switches. It's just an on-off, and we'll look at some of the basic physics behind it. That MOSFET 1 is mostly what we're going to do today. We'll do CMOS Digital 1 on Wednesday. By the time you get done with that class, you will be able to design a CMOS circuit to build any logic function you want whatsoever, given A or B, A and B, A or B ANDed with C. You know, just pick a random function. You can. It's a pretty easy trick once you get the on-off of MOSFETs. Then we're going to get deeper into the MOSFET, looking at the current voltage characteristics, the 3 regions of operation, and the weird creature that we call PMOS. And then we'll get into some more CMOS digital, where we have to think about the CMOS having, the transistors having both delay and having electrical characteristics. which even as a digital designer, you've got to think about the analog considerations. And then we'll get into some MOS analog amplifiers. And this right here, this couple of weeks here is pretty much the first 2-3 weeks of EE280 is where we're going to head with this. And then we go deeper into each one of these topics. I got an email on Friday, and I'm going to have to gloat a little bit. Guy's they've got a company down in Tucson that does data acquisition. And he's like, I have been looking for quite a while to find students who actually know something about analog. Nobody's teaching it anymore. And he goes, when I went to NAU, I found what I was looking for. Now I need to hire somebody. Can you please just find me somebody? Even digital circuits, you've got to know a little bit of analog. There's some stuff I saw in the high-speed lab at Micron that was like hardcore RF. It was amazing. I want to go over this because I didn't realize that people didn't know this until I started. Oh, I'm going to need a white marker. Draw. Let's make it white. Okay. People didn't know this, but it's kind of like built into all the voltage nomenclature. When we're dealing with transistors, most of the voltages have, oh great, it's doing this again. Drop and touch, go back here, do things at random, scribble on my screen, give up. Use my finger. Ah, okay, so my finger works. Okay, we have two subscripts like VGS or VDD. Now these have very specific meanings to them. VGS is the same thing. I take a voltmeter, I put the positive probe at the gate, VG. I put the negative probe at the source, which is VS, and I measure the difference between them. So VGS means the voltage at the gate relative to the source. It's VG minus VS. So when I talk about VDS, and this is big V, big D, big S, I'll get to that in 380. This is the same thing as the voltage at D with respect to ground minus the voltage at S with respect to ground. Voltage is always a potential difference. Now, if I get this double subscript like VDD, these double subscripted things are usually referring to power supplies, unknown name in Colorado. Okay, the VDDs are usually referring to power supplies. Now, for a MOSFET, the D stands for drain. So this is usually the DC power supply because the drain of NMOS transistors typically goes to the DC power supply. Sometimes people call it VCC, and you'll see VDD and VCC used interchangeably. And that is mainly because back in the day when we were dealing with bipolar transistors mostly, the equivalent of the drain was called the collector. And engineers just get lazy. They tend to call it, well, it's always been VCC. So with this MOSFET circuit, we're going to call it VCC. And you see them used back and forth. Just be consistent in your design and you'll be okay. If I just get one subscript, like this VG, that means the voltage at the gate with respect to ground. So that negative end of your DC multimeter would go to ground. So this, get that squared away because, yeah, we'll be using that a lot. And sometimes I'll remind you. This is what a MOSFET looks like, or what it looked like 5 years ago. Cedra Smith hasn't caught up with FinFETs yet, so we're still teaching planar MOSFETs. The ideas behind that are still valid. How a MOSFET works is still valid. The technology just looks a little different. I'll show you some pictures of that. And when we get into 380, my the guy I work for in the lab, Dr. Cambeau, will come in and talk to you about how they're shrinking the technology down to 3 nanometers, and now it's 2 nanometers, and he keeps up with that pretty well. So it's a 4-terminal device. What I've got here, what does MOSFET stand for? Let's see if I can write. Oh, yay, I can write. MOSFET. And my throat's no longer cracking. Metal. Not much. Oxide. Semiconductor. Field effect transistor. I'm going to show you where the metal is. The metal is up here. It's this layer called the gate, right about there. There is a very thin layer of oxide right there. That's the oxide part. And then the bulk is the semiconductor. So that's the substrate down here. That's a MOS capacitor. And we're going to use that MOS capacitor to create charge in this region so I can conduct from end to end. Now, if you look at this, I'm getting way ahead. The way this thing is usually biased is, this is an NMOS. The body's grounded. The source may be grounded. And this is kind of a typical thing. The drain's going to some DC, positive DC voltage. I'll just talk about those 3 terminals first. So what's going on here is the drain. If you look at this, the first thing that you should notice is there's also these PN junction diodes in here. So I've got an N+ region and I've got a P-type substrate. The junction between them is a diode. Now the drain, the N side is at a higher voltage than the P side. So no current's going to conduct. I have a back bias diode there. And over here between the source and the body, if they're both connected to ground, I also have a 0 bias PN junction. No current's going to flow through that either. So it doesn't look very useful in that perspective. This capacitor, I'm already calling it a capacitor. It looks like a capacitor, doesn't it? I've got a metal plate. I've got an oxide, which is kind of like a dielectric, and I've got a semiconductor, which is kind of like another metal plate. It's a capacitor, and we're going to use the capacitance of that gate, of that MOS structure, to change the dynamics of this device. Okay, and we'll explain this in a minute. Try not to get too far ahead of myself. The 4 terminal names, we might as well throw those in there. G stands for gate. The D stands for drain. Try to keep this in the white so I don't have to change colors. S stands for source. And B stands for body. Most people, most circuit diagrams you see, they have 3 terminals for a transistor. People forget about the body. And one time it happened quite disastrously. I was given this part to test, and the chip designer, the overall chip design for the whole high level thing, they forgot to tie down the bodies of all the transistors. Sent this, it was for the SIRTIF, the Space Infrared Telescope Facility. So they were going to send this chip, it was supposed to be part of the focal plane for that device. They sent it out to like 6 or 8 different labs to test. and 7 of them sent it back and said it's a POS. In about a week, it just doesn't work. And they no explanation. And I was told by my boss that I was paid for 6 months of testing. I had to test it for 6 months. I wrote an interesting paper on it and got a job at JPL out of all this, but because I figured out what was wrong. We were the only ones who bothered to actually test it. Okay, and it was a really easy fix too. You just have to ground the body. Now, if we look at this, this is a picture of what the transistor looks like on the side. Normally, when you're doing VLSI design, when you're designing these, you're looking at the top view, kind of looking down at the gate, and you see the different regions of operation, the different metals and the different chemicals you put in here. Sometimes they want to see what's going on from the side view, and it's a very destructive, and that's called a cross section, very destructive testing. You actually take the chip and you take a saw to it and you slice through it and you look at this cross section underneath an electron microscope. That's what they're trying to do in lab 4 right now in EE280. Not actually, just imagine it. No, it doesn't involve actual electron microscopes. That's for grad school. Okay, so I've got an NMOS device here. I'll try to write small. This is the metal. This right here is the oxide. And the critical thing about that is the thickness of the oxide. This is the semiconductor. In the case of NMOS, it's going to be a P substrate. For the drain, I'm going to put a P plus diffusion in. It's heavily doped. No, it's an N plus diffusion. This is an NMOS. It's heavily doped. The plus means it's got heavy doping, and that lowers the resistance of the contact. And we're thinking of that as being a contact resistance. So we want it to be as low as we possibly can. Oh, good. The G is the gate. It's going to be eventually, I'll explain where the gates connect. I haven't talked about that yet. That'll be the magic that turns this transistor on. Okay, so the gate's going to be up here. It will eventually have to be connected to some kind of voltage source. I've got the metal, I've got the oxide, I've got the semiconductor. I've got another N plus diffusion here. This is for the, whatchamacallit, the other terminal, the source. And the body actually wants to contact into this P substrate, so I'm going to make it a P plus diffusion. And this is called an NMOS. And I'll explain why it's called an NMOS, because these are N's. Now, if I want to build a PMOS, I usually want to build these on the same substrate. So what I do here, we might as well just go for broke here, is I put in an N well. And an N well is an N diffusion. So this will be N type. And this would be my PMOS side. You put, there's no such thing as a CMOS transistor. Let's get that out of the way. There's the circuits that use both PMOS and NMOS transistors are called CMOS, which is complementary MOS. But there's 2 distinct types of transistors within here. Same thing over here. I've got the gate. I've got the, let me get this right. I've got the body. The body is going to be tied to the N well. So this is N plus. This is going to be P plus. This is going to be P plus. This is the body. The body is going to be tied to the source. Yes, okay. And this is the drain. I got all the symmetry right. And we still haven't talked about how they operate, how I turn them on. They're obviously off for everything we've done so far. Now the NMOS and the PMOS, the N stands for N channel. and the P stands for P channel. And what I have to do in order to get these things turned on and conducting current is I've got to somehow form a channel of electrons between these two N+ regions to allow it to conduct. And that's what the gate's going to be for. I know I'm leaving a lot to the imagination. The huge P, no, because the P-type substrate is very lightly doped. The P+ is a contact to that lightly doped P substrate. Right, so the P+ under the body terminal. So this is a P+, this is the connection to the body. This is the substrate. It's lightly doped, but this gives me a low resistance contact into that substrate. That's the only reason why I dope it heavily. Okay, we haven't talked about how it works yet. Is that not shown in the previous slide? So let's look at the previous slide. And no, yeah, you're right. The body connection is missing on this slide. And it's very commonly forgotten until your circuit doesn't work in the 380 lab. And then all of a sudden you realize, oh, I got to tie the body somewhere. Okay, the different dimensions we're looking at here. We're gonna, when we get this thing working, and I haven't told you how that happens yet, we're gonna have current flowing from between the drain and the source. So this L is the length. It pretty much modulates how long your wire is between the drain and the source. The width of the transistor is how wide is the gate. Oh, now I really want light. How wide is the gate in that dimension? And the key parameter you have as a circuit designer, if you're not the process engineer, to control the characteristics of the transistor are the W/L ratio. It's the only thing you can control. There's a lot of good reasons to make W bigger, but there's not many good reasons to make L bigger. In fact, L being bigger makes most devices work worse. So you want to get down to the minimum L you possibly can. Present day processes, the oxide thickness across here is about 4 nanometers. That's only about 20 atoms thick. It's what it is. Not a lot high precision in this processing. The oxide, the actual oxide, the material we put in here, is probably nitrated hafnium silicate, which is also going away. Which color am I? Hafnium silicon, yeah, nitrated hafnium silicate. It has a relative dielectric strength of 20. Now for Cedar Smith, they're still back in the dark ages of about, this is probably 10, 15 years ago, of using silicon dioxide, which has a relative dielectric strength of around 4. The difference between those two, or the difference between being able to make that oxide thin and still have a significant amount of capacitance. They're actually going away from the hafnium now. They're using rare earth materials that have an epsilon relative in the 40s, especially for some of the really advanced processes like Samsung and TSMC do. Now, people interchangeably, it's epsilon takes a long time to say. So interchangeably with epsilon, they refer to the K of the material. I don't know where K comes from. I just know it's epsilon. Yeah. And you'll hear me do that, flipping them back and forth occasionally. If you ever hear Dr. Cambeau talks, he talk. He just uses K. Now the L, this is the number that's been shrinking. When somebody talks about, Intel talks about their new 7 nanometer process, and they're really excited about that. The 7 nanometers they're referring to is the L, the minimum length they can make the transistors reliably. Intel's been falling behind. Back in the 90s, every company had their own semiconductor fab. And it's been getting harder and harder and more exacting. And now machines that used to cost them, you know, you'd have to set up this line with maybe like 20 machines, and each machine would cost you a couple $1 million. Now it's each machine costs you $100 million. And to get the recipe right is really difficult. Intel's fallen behind. They're stuck at 7 nanometers, and they are behind on their launch for 5 nanometers. And they got stuck at 9 nanometers for a while. Micron's still doing their own processing, but they are at 9 nanometers because they need the larger size for their memory cells so they can get the capacitance for the DRAM. The only 2 companies that are really seriously hitting or are in competition right now are Samsung and TSMC. And what most companies who sell integrated circuits have been doing is they do the design themselves in-house, and then they ship it off to Samsung or TSMC to fabricate it. That's the way Apple's gone, that's the way AMD's gone, and that's the way Intel's about ready to go. TSMC is building a big factory down in Phoenix on the northwest side. They're expecting to hire 150 additional new grads this year. You've got to be willing to spend like 18 months in Taiwan being trained. Apparently the town that it's in, I've been told, has the best food in Taiwan. And then you come back and you'd work in Phoenix. So, and then next year they're expecting to hire 500 new grads. And so it just keeps getting going on. But Samsung and TSMC are the 2 that are really seriously pushing the technology. They're down to the 3 nanometer node. The factory that's going into Phoenix will be a 5 nanometer starting out and may go down to some of the smaller dimensions. Generally, the minimum width is the same as the minimum L, but we don't worry about that because we always want to make L shorter. And there's tricks they're doing to make that happen. Yay, how it operates, what I've been trying to avoid, Jordan. Okay, we start out here, and we've already talked about this. We want to be able, about this part of the operation, we want to be able to control the drain current. So if I start off here, and I have the source grounded, and the body's grounded, and the gate's grounded, and I apply a voltage between the drain and the source, VDS, what's going to happen? I have a positive voltage at the drain. I have, that's the N side. I have a less positive voltage on the body. So this is reverse biased. Nothing's going to happen here. I've got 0 voltage across this one. So this is 0 biased. No current there. No current there. A reverse bias diode has some leakage current, so I may see like IS, really small leakage current flowing through this device, probably in the wrong direction. There's not going to be any drain current flowing for purposes of 280. IS is pretty much close to 0. This is the transistor in the off state. And all we'll get to today is on and off. Can we possibly have an on slide here? Yay! Okay, on. How do I turn this thing on? Okay, so I've got a voltage from the drain to source. I've got a voltage from the gate to source here, and the body is at ground. Okay, we've already pointed out that this is metal oxide semiconductor. It's a capacitor. Q equals CV. It's a capacitor, and across that capacitor, I have VGS on one side and ground on the other. So the voltage is VGS. The capacitance isn't zero. So I'm going to have some charge accumulating. That's what capacitors do. They store charge. So since this is the positive side of the voltage, I'm going to accumulate positive charge on this side of the capacitor, which means on the bottom plate of the capacitor, I'm going to accumulate negative charge. So I have to put a big enough VGS on here to accumulate enough charge across that capacitor that I have this little channel here. Remember, we call this an N for N channel. I have this little channel here of NNN that current can flow freely. So I use the capacitor to build up charge in the channel, negative charge, which allows me a path for current to flow. As I increase VGS, I'm just going to get more and more charge here, up to a limit, but we won't talk about that yet. It's going to take some amount of voltage here to get enough charge to form a channel, and that's called V threshold. I think that's the next slide. Okay. So the minimum amount of voltage. Oh, great. No. Okay. So I think I know how that triggers now. The minimum amount the minimum amount of voltage that I can.
I have a quick question.
Oh, please.
You said that on the last slide. Hold on, just lost my train of thought. Increasing voltage increases the charge.
Yeah, increases the voltage. Increasing the voltage increases the charge.
Okay. All right.
Yeah. Okay. So there's a really basic parameter for the transistor, and this is called VT or VGS on, or sometimes it's called V threshold, or sometimes I write VTN to indicate it's the threshold voltage for the N channel device, which will be different than the threshold voltage for the P channel device. It's the minimum amount of voltage I need to put on the gate to form a channel that will allow current to flow. So there's two states for this transistor so far. We'll get to the third state later. Not today. If VGS is greater than the threshold voltage, then I have that negative charge channel that forms. Current can flow from drain to source pretty much freely. The transistor is on. And in this case, it's a very small resistance, because the resistance is I've got NNN. It's just the resistance of whatever the semiconductor is. Fairly small. I would put the equal sign there and not here. Okay, but never mind. If VGS is less than VT, there is no channel. Current cannot flow. The only thing you're going to see is leakage current, and the transistor is off. In this case, it's an open circuit, which is a very high resistance. So as long as VGS is greater than VT, it's on. I've got a channel and current flows. And we're treating this like it's a digital 1 or 0. In fact, there's a lot of gray area in between there. The symbol for the MOSFET if we look at the diagram over here, you can see we've got the gate, kind of corresponds to the gate up there. We've got the source over on one side and the drain and the body. That is not a way a sensible engineer would draw a MOSFET in a circuit diagram, though. They're going to draw it like this. We've got, how much time? Oh, yeah, we got plenty of time. They've got the drain goes on the top, the gate over here, or on the other side, the source and the body. There is a convention and a pattern to the way electrical engineers draw circuits. And I've never seen this in a textbook, but it's important. You have a schematic. One thing that people normally do is they put the higher voltages at the top and the lower voltages at the bottom. If you draw your schematics like this, other people will have an easier time reading them. And when you look at other people's schematics, they'll make more sense. On this side of the paper, I put the inputs. And over here, I put the outputs. And the reason why this is important right now is because when I draw my MOSFET, my N-channel MOSFET, the drain voltage is usually going to a higher voltage. The source voltage is usually going to a lower voltage. Oh yeah, and the other thing is currents flow downhill. So I flows downhill. So when I put the circuit in there, this is the way the MOSFET's usually drawn. The gate's over here. This is the drain, this is the source, and a lot of times it'll just leave the body off the schematic. That little arrow right there, this little arrow right here that I've attempted to draw, indicates the direction of current flow. When current flows in this device, it's going to be flowing like down through here. So it's flowing downhill. When I draw a PMOS transistor, and I'm getting a little bit ahead of myself, PMOS transistors look like this. This is the little arrow, and they're drawn upside down. This is the source. The little current arrow always goes on the source. This is the drain, and this is the gate. Again, this is the higher voltage is going to be on the source of a PMOS, and there's a little bubble right here too. And current's going to be flowing downhill. So PMOS are always drawn upside down normally. Talk about the PMOS days. Well, at some point you realize PMOS is upside down NMOS. I actually had to build an entire circuit once, an integrated circuit entirely using PMOS transistors. They're lower noise, and astronomers are really like low noise. But also the logic's inverted. And I am a if you've been in my one-time class, you know this. I am a right-thinking, positive logic kind of person. So all of this is negative logic. And the guy who was actually doing the layout and the design, he was in Santa Barbara, and we would get on the phone. And it would just, we could not talk. We would almost start yelling at each other. Yeah, I want that on. Oh, okay, so you do this. No, it's off. No, I want it on. And the on-off thing just completely perplexed us. And finally, we came up with a solution. Is we put inverters on all the inputs and outputs of the chip, and suddenly we could talk to each other. It converted it all into positive logic, so. Yeah. Jim Wooley. Okay. So we wanted to, really basic, we just want to determine, are these MOSFETs on or off? So what I need to do here, first thing I want to do is I want to label the gate, the source, and the drain. And all I have to figure out is what VGS is. So for A, I've got my gates at 0.2. So VGS, it's going to equal VG minus VS. And that we need to check and see, is that greater than or equal to VTN? This is an NMOS. So VG minus VS is 0.2 minus 0 is 0.2. And is that greater than, what's my VTN? It's 0.4. No. And the answer is no. So this one is off. So go ahead and take a few minutes, and the gate and the source are still the same. This is still the gate and the source, all drawn in the same polarity, and figure out if B, C, D, E, and F are on or off. And I'll look at the chat. And I'll move that out of the way so you can see that. The TSMC is going to be a 5 nanometer is their initial, what they're opening up with, and they may go down to smaller devices later. I think they're building their 3 nanometer fab in Taiwan. If the source and drain are both grounded, is the current flowing? No, there'll be no current flow. Even if you have VGS is greater than 0, if VDS is 0, the current will be 0. We'll look at that when we get to MOSFET 2. We'll actually get equations of current. But yeah, you need some voltage difference between the drain and source to get the current to flow. Okay. 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 So B, is it on or off? It's on. VGS is 1.8 volts, so that is on. Okay. Oh, great, not this. Go here. Oh, great. I hate you. Okay, I'll draw with my finger. Oh wait, it's off of that. Oh, just pick one. No. Okay, we'll just draw I'm just gonna draw with my finger. So for B, VGS is 1.8. So that one is definitely on. It's greater than 0.4. C, my VGS is 0.9. So this is on. D, VGS is 0. So this one is off. E is on because my VGS is, whatchamacallit, 1.5. Oh, now it's not. Now I can't draw with anything. Oh, there it goes, on. And F, VGS is 0.6 minus 0.3 is 0.3, not bigger than 0.4, so this is off. In reality, that will be conducting some current, but just not as much. We'll just call OF is good enough for off right now. Okay. Oh, great. I just want to throw this thing right now. Okay, I'll use my fingers. Now PMOS, it's kind of the same idea. Now I've got two P regions here. Thank you for the source looks like it's only coming from the gate on. Oh, okay, I see, okay, never mind. I think I'm okay on that one. For the PMOS to form a channel, I've got to get positive charge. Oh, come on. Let's see with the, I got it. Somehow I magically got it out of that loop. Okay, so for PMOS, for the channel to form, what I'm going to need to do is I need to form a P channel down here. I've got two P plus regions. So in order to get a path for current to flow, I'm going to need to draw positive charge into the channel, which means I'm going to need negative charge on the other side of that gate of the capacitor, which means my VGS must be less than 0. My V threshold for a PMOS device is going to be less than 0. It'll be a negative number. I have to get negative charge at the gate, and I need to get positive charge at the channel. Now, this is the way most people actually draw. Oh, great, you're kidding me. Okay, this is the way most people actually draw at PMOS transistors, with the source going on the upside and the drain going on the downside. We just talked about that, and the current arrow flowing down. You can flip it over, but I've very rarely seen it drawn like that bottom example. Another thing that's going on with PMOS is, again, we've got these PN junctions in here, and we have to back bias these diodes to keep current flowing in the diodes and just completely messing us up. So in order to do that, I need to make this N-type side the most positive voltage in the circuit. So typically I'm tying the body into VDD. NMOS, we tie the body to ground. PMOS, we tie the body to VDD. You'll hear me repeat that over and over again in the 380 lab. But when your circuit's not working. The body's tied to the highest voltage and the ground because I've got to keep those diodes reverse bias. And again, my gate voltage is going to have to be negative in order to make this thing work. So what's going on in here is, here's a typical value. Oh, good, it works now. VTP, -0.4 of a volt. The only thing that really changes, the numbers I'm giving you right now, when you get down to those smaller processes, the 3 nanometer processes, they have to run them at lower power. 0.8 volt logic, 0.6 volt logic. In order to do that, I can't have plus and minus 0.4 of a volt for the threshold voltages. What's happened to the threshold voltages is, as the device dimensions have decreased, so have those threshold voltages. So now you're talking about 1 to 2 tenths of a volt. They're just smaller numbers. If you understand how all this works, changing the numbers isn't that big of a deal. A lot of the times it's just changing your spice deck. We'll talk about that. The gate voltage must be 0.4 of a volt below the source for the channel to form. It doesn't mean that I have negative voltages in this circuit. What I do here is, what's a good color for this? I tie the source to VDD. I tie the drain to ground. All I have to do here is pull this to, let's say we ground the gate. Then I'd have 0 volts at the gate. I'd have, this is 1.8, 1.8 volts at the source. The voltage difference between those two, VGS, is 0 minus 1.8 is negative 1.8 volts. So I don't have to put negative voltages in the circuit to use PMOS. I just need to have the gate at a lower voltage than the source. This is the source, even though I tied VDD to it. This is the drain, and then that's the gate. It's just the way you have to hook up PMOS circuits. Okay. Big thing here, we need VTP less than, okay, so let's switch. Oh, to do this? Yes, okay, it worked. We need VTP is negative 0.4 volts. Now I've drawn the transistors in the correct orientation for my worldview and most schematic designers. I've got the gate here, I've got the source here. So what we need, the question we need to answer is VGS less than VTN. If that is true, then this transistor is on. My VGS, VG minus VS in this case is 1.6 minus 1.8. Is that less than negative 0.4? So this is negative 0.2, less than negative 0.4. That is not true, so it is off. So go ahead and take a few minutes and figure out H through L. This is so much more relaxed. I got a whole day to do this, and I'm not rushing to get into digital circuits. I should schedule this class like this more often. Okay. Oh, we are recording. Negative. This one is. Off. 3 minus. Oh, yeah. Okay. Is everybody okay with that? Anybody yelping at me in the chat? Oh, somebody said something. Yes. Okay, good. So fairly simple so far. Oh, yes, my favorite part. Oh, you don't understand how emotional I get over the circuit. Here we go. Okay, we got two conditions here. If it's off, there's no channel and I have a very high channel resistance. If it's on, there is a channel and I have a low channel resistance. Let's look at the resistive circuit on the right first. Let's say Rn is something like 1 ohm. And let's say RP is something like 1 gigaohm. Not unrealistic. Okay, what would my V out be? You could use a voltage divider. I've got 1.8 times 1 over 1 plus 1 gig. This is going to be pretty close to 0. Let's change colors. It's something that's not white. Now I switch this around. Let's make this 1 ohm and let's make this 1 gigaohm. Now when I want to find the voltage output, I use my voltage divider. The answer is 1.8 times 1 gig over 1 gig plus 1 ohm. This is going to be pretty close to 1.8 volts. Now this is the trick with the inverter. I know it's in the next slide, so I'm going to resist the urge to do this. I can take, when one of these is on, I have a really low resistance. And if I turn the other one off at the same time, I have a high resistance. It's just like this voltage divider. And I can flip those conditions. I can make the Rn the high resistance and make the Rp the low resistance. Okay, I finally get to do it. You'd have no idea what an inverter looked like when I took this class in 1985. It was this horrible thing with BJTs and diodes and resistors in it. You had to actually calculate voltages and currents. It was horrible. Okay, this is why CMOS is so wonderful. Okay, remember this from 110. It's an inverter. That's what this circuit is right here. 2 transistors. If I actually wanted to build the inverter, the way I do it is I build it with 2 transistors. Now let's look at 2 cases here. I'm going to make VN 0 volts. VDD is like 1.8, something like that. It'll stay the same. If I have 0 volts on the gate of an NMOS transistor and the source is grounded, my VGS is 0 volts. This one is off. It is a high resistance. If I put 0 volts on the gate of my PMOS, now my VGS is across here is negative 1.8. So this is on. It's a low resistance. And if I go back to my voltage divider rules, my high resistance, I've got VDD tied up here. I've got a low resistance to VDD, a high resistance to ground. This is going to come up to be about, oh great, 1.8 volts using my finger. Okay. Now we flip it around. So we've got to change colors, of course. Let's go to, we got to use something fairly light, medium. Okay, we're going to use green. We put, I use my finger. Oh, good, it worked for some reason. I put 1.8 volts in at the gate. So I've changed a little bit in time later, I'm changing the voltage. I've got 1.8 volts gate to source on the NMOS. This one goes on, so now it's a low resistance. When I look at my PMOS device, I've got 1.8 minus 1.8 is 0. So this goes off. It becomes a high resistance. I've got a high resistance to VDD, a low resistance to ground. So my output's going to be 0 volts. If my input's 0, my output's 1.8. If my input's 1.8, my output's 0. I built an inverter, 2 transistors. It's beautiful, it's perfect. I'll show you the TTL inverter. I think that shows up in the next set of slides. We'll talk more about this one. That's the whole point of Wednesday. Okay, last thing I want to talk about, and why did I have to throw this at the end of the slides is beyond me. Other than when you see this on the homework, don't say you never saw this before. This is a slide that you want to like point out to yourself. And thank goodness I actually put this in here. Yeah. Okay. We got this epsilon, what I called K before. Epsilon relative for silicon dioxide, which will be for all the problems in the coming from the book, is 3.97. We can change that number to modernize it a bit. The epsilon refers to, it's like the relative, it's like the capacitance of free space. Free space is a dielectric, air is a dielectric, and air looks kind of like free space as far as its dielectric strength goes. This number is, it's a fundamental constant of the universe. It's called epsilon naught. Whenever I don't want to have to repeat 4 times 8.854 times 10 to the minus 14th over and over again. So we just kind of take this number out and make it a separate constant. So any equation you see that has epsilon in it, you need to think it's got 2 parts. It's got the relative strength, like it's a number, reasonable number like 4 or 20 or 50 even, times epsilon naught. You always got to remember to multiply it by epsilon naught. If your answer is off and you've got something that has gigafarads per millimeter squared, you can pretty much guess that you've forgotten to multiply by epsilon naught. I want to go through this problem because there's a lot of dimensional stuff in here. The formulas are in the slides, but I'm going to switch to bamboo paper because I really worked these out, and I've got the numbers on there. So whatchamacallit, I got the numbers written down, so I know what's on the slides. And this will be the last, this is basically effectively the last slide for today. So it's the last thing you got to put up with. This will get more important as we get into the analog and we get deeper into the operation of a MOSFET. So there's this formula here for COX. Why is this not working now? This one's easier to do. So COX is given as epsilon ox over TOX. Every time we see that epsilon, we've got to, hold on. Okay, never mind. We got to remember that it is epsilon relative epsilon naught over TOX. Now, epsilon naught And I'm going to put the units in here because the units are kind of what's going to bite you on these equations. Epsilon relative. Okay, good. I got. Sorry, I'm having technology issues. Epsilon relative is 3.97 for silicon dioxide. Epsilon naught is 8.854 times 10 to the minus 14th. And this is farads per centimeter. And this is why I'm putting these units in here, because they're going to be important. TOX, we were given that this was 4 nanometers. In order to make the units match up, I have to convert that into centimeters. So 4 nanometers is 4 times 10 to the minus 7th centimeters. Now I'm going to have an answer that's at least in something reasonable. And I punch that into my calculator. And what I get is 8, wait, let me get the right one in here. 879. And it comes out to be 10 to the minus 9. So this is nanofarads per centimeter squared. Okay. The next number that we had to calculate, we'll talk about this transconductance parameter later. It's basically the gain of the it's related to the gain of the transistor. We have 2 types of this. There is Kn. I just want to talk about units. Kn prime, which applies to every single transistor that I get out of the process on that day. It's called the process transconductance parameter. Thank you. Nanometer is 10 to the minus 9th meters. Yes, you should learn those. You need to learn those. Nanometer, process, micrometers. I go atto to exa. Is pretty much everything I've ever had to use. Atto's 10 to the minus 18th. And an atto amp, which was what we were measuring, was atto amps. An atto amp is basically, it's about 5 electrons per second. Yes, and we had to measure current, and we were actually measuring current in electrons per second because it sounded cooler. Kn prime, okay, so Kn prime is the process transconductance parameter. All of this will make more sense later, but I want to go through these calculations in detail at least once. And I have time to do it now. Parameter. So Kn prime, we're given this little formula here that looks deceptively simple. Kn prime, and this is on the slides, equals something called mu n, which is the mobility. We'll talk about that later, times Cox. And Cox is the same thing we've just calculated right here. And we're given on that slide a number for mu n. And usually the TSMC or whoever makes it will give you that number when you get your chips back. Or if you're working at TSMC, you're the guy who has to measure that number. So reasonable units here are 450 centimeters squared per volt second. Well, yeah. I think we've talked about mobility a little bit in here. Have we? No, we haven't talked about velocity in here. Okay. 450 centimeters squared per volt second. So we'll just take that on faith right now. And believe me, I'll talk more about mobility later. And Cox, we just calculated, it's nanofarads per centimeter squared. Reason why I wrote these units down is I wanted to make sure those length units cancel out. If I put typical units for Cox might be femtofarads per micrometer squared. If it was in those units, I'd have to do some conversion before I'd multiply it. So my centimeter squared cancels out. So I get I do this calculation and I get this screwy set of units at the end. 395 microfarads per volt second. Okay, no relation to reality at this point. I just happen to know that a farad per second is an amp. You could, if you were like me, you go home after this and you do the dimensions and you figure it out. I'm going to leave that to you guys. This is how I wasted my time when I was your age. So 395, a farad per second becomes an amp. So this is micro amps per volt. And we know V equals IR, so the units of resistance, ohms, are volts per amp. So that's like a conductance. It's like 1 over ohms. We could also put that in like micro mhos. And that's just 1 over ohms. Typically, they give it to you in amps per volt. Now, the next thing you want to do is you want to find the gain of your actual transistor. So that is, and my seniors just got a problem with this, and I bet you I'll get questions about it, even though they've been doing this for 2 years. Kn is Kn prime times W over L. So Kn prime gives you the gain for the whole process. If I know the specific size of the transistor, it's W over L ratio, I can calculate the gain of that specific transistor. That's what's going to show up in the current equations, is Kn, or Kn prime W over L. Sorry, I'm getting excited. Mhos. You did not have me for 188, Jordan. Yeah, conductance will show up a good bit when we get to these transistors. We have a what we're going to have, do I have time for this? No, I don't. We have a dependent current source in there, and it is GM VGS. GM is a conductance, and it does show up lots of places. Just have to, yeah, in transistor theory. Yes, Mhos. Sorry, I have a whole, I'm going to have to get out my Mhos law sign. Nobody remembers the Three Stooges, though, so it doesn't help. Kn, we got a number for Kn prime anyways from the last slide. It was 395 micro amps per volt. And the W over L for this particular transistor was 1 micrometer for W and 0.18 micrometers for L. So those micrometers are going to cancel out. As long as they're in the same units, W over L is dimensionless. And so what we've got here is we have our Kn is also going to be, it's 2.2 micro, well, that doesn't seem right. Somehow my calculation doesn't seem right, but I'm just with this. 2.2 microamps per volt. I'm going to check that. I have a calculator here. Wheel calc. 395 divided by 0.18. This has got to be off. Yes, it is. It should be milli. That's what's wrong. Milliamps per volt for that particular transistor. Okay, back to PowerPoint, and we're almost done. I thought I was going to get done. I never get done early. Decimal points are important, whether I say 2.2 microamps per volt or 2.2 milliamps per volt. We're off by a factor of 1,000. It's going to make a huge difference in your calculations. Go back and review those multipliers. Kilos, 10 to the kilo, mega, giga, tera, peta, exa. And then on the other side, it's milli, micro, nano, pico, femto, atto. Review those and get those down. It's the way engineers talk to each other. It's important. Okay, I'm done. Let's see who's, oh, people who were missing. Ibrahim, are you here? Or Zach Price? We will stop screen sharing. And somebody's chatting at me. Mobility is actually the proportionality constant between velocity and electric field. It's defined by the equation velocity equals mobility times electric field. So I put a bigger electric field across something. I get a bigger, my electrons move faster. Up to a certain point. They can't move faster than the speed of light. Okay. Okay. What kind of project is it, Jordan? Is it programming? No, okay, good. Yeah, I'm in. Yes. Yeah, I can help you guys out. Just send me the proposal. I'll take a look at it and see what if there's anything I can add. Maybe we can have a Zoom meeting with you and the other 3 students. I'm sure it would thrill the assistant dean to have. Never mind. Yeah, we can do that. Okay, good. That sounds good. Okay.